Okay. Hello, everyone.
I mean, they can't hear us. Right?
No, I don't think they can hear you. No,
I'm
yeah.
looking for wireless earbuds for like my computer.
Uh,
Everyone makes them for phones, but they
okay,
don't
nice.
include. Yeah. Okay.
So that last lecture, like Yuri gave, he went over two problems: edit distance and Bytonic Euclidean traveling salesman problem. Really difficult. At least the second one was really difficult. The first one we'll be going over today. One I have. Gary take had to wait till next week for him to look over the recurrence relation for the DP table. What do you guys think? How hard was it?
Oh, the second one? It was so easy, man.
Okay, David said it was easy. Okay.
I'm just kidding.
So David will be teaching this lecture today since he said it was easy and he knows how to solve it. He's going to do the second problem, right?
I'm working twice this week. Okay.
Yeah.
Someone do it without even realizing?
Yeah, Ricky solved it recursively. Yeah.
Oh my god.
Yeah, Ricky solved it recursively. I guess we can talk about it. Yeah, we can talk about it. So obviously, like we had all the nodes, right? And then what Ricky did, he started at the first node, which is the node all the way in the far left. And then, so he started at 1, 1. And then he added another node. Let's say the next node is going to be 2. So then he did 2, 1, or 1, 2. Where the first one represents the top path, and then the second one represents the bottom path. So with this, he was able to figure it out, and he did it. He submitted it to the problem on the website, and it actually got accepted. But figuring out the recurrence relation for the DP table proved to be incredibly hard. We tried to do it together, and we still couldn't figure it out. So I guess to a certain point or extent, we understand Gary's struggle yesterday. That's straight? I feel like this is not straight. Huh, okay. Hello, Azar. Thank you for coming.
Hello.
How's your foot? How's your foot? Better? That's good. Okay, just drawing the edge for my workspace. Cool. I feel like this is really not straight. There we go. So have you guys ever heard of the problem before, edit distance? That's one nod.
Maybe, so 0.5 maybe.
0.5, all right, 1.5. Okay. 1.5. 0.5 coming from Azar. Hey, Demba, how's it going, man? How about you, Alejandro? Have you heard of edit distance?
What is that?
The problem?
I've heard of it.
You've heard of it?
Yeah.
Do you know like the problem description?
Yeah.
You do? Okay, so that's 2.5. How about you, Demba?
What, edit distance?
Yeah.
I think I've heard of it, but isn't the one that you way too much of the thing?
Yeah, exactly.
Yeah.
All right, so we got 3.5. Cool. That's good. I think I have to redraw my borders. You know what? I can use this whole thing. That's fine. But for this one, it does have to change. Yeah, this one's a little bit closer. One here. Cool. All right, so that's the problem we're going to be going over. We're going to be doing edit distance.
Is it going to be getting the number difference or the actual string matching?
So yeah, that's a good question. I'm going to get the differences, or how many edits we need to make to change one string into another, or we're going to get what was the other thing?
String match, the match string.
Yeah, or are we going to get the match string? The match string is either string 1 or string 2. So we could set it up in the DP table so it memorizes what steps to take.
I mean, the diff.
The difference?
The diff, yeah. Like the Unix diff.
Oh, the Unix diff. Yeah, no, we're not doing Unix diff.
Oh, so we're just getting the number.
Yeah, we're just getting the number. All right. So yeah, that's the problem we'll be going over because, like I said, the other problem that he did is really tough. I just don't know how to figure it out.
Plus, he didn't finish that anyway.
Yeah, Ricky did do it recursively. Yeah, genius, of course. Woo! the genius that he figured it out recursively. But the DP table recurrence relation, like I said, is tough. But yeah. So we'll wait till next week, and then I'll struggle to do a review on that. So yeah, I'm just gonna push off my responsibilities till next week, which is fine. I'm a college student. That's what we're used to, right? All right. So, cool. Let's start off simple with two strings. Let's call it A and B. Let's give them variable names A and B. The first string, let's say it's ACE, ACE. Let's say the second string is APE, APE. How many edits will we have to do right here already to change ACE into APE? Wait, or either way. Yeah.
What is an edit?
Okay, good. That's a good question. So what is an edit? An edit, for this problem at least, is we can either replace a character or make a gap in one string to fill that up with any other character. So for example, let's say this was ACE, let's say it's ACE and APE, that's exactly what it is. The edit we would have to make here is replace P with C to get B equal to A. Or let's say B was just A and E. Here we can do two things. We can replace the E for a C and then turn it into AC. And then in the end, put a gap, where that gap will be filled by the character E. Or we can also do that requires how many edits? 2? Okay. Yeah, this would require 2 edits, but the better choice is to do A, make a gap, and then E. This requires 1 edit. So those are our choices. Either replace character or put a gap. Cool? Making sense so far? Yeah. Let me see if there's anything in chat. Eliso and David Acosta. All right. Monkey. I see Azar. I see Azar started that trend. So okay. Something new. That's fine. So let's write down our possible moves, which is replace or create a gap.
Are we allowed to add characters and delete them?
Are we allowed to add characters and delete them? Yes, we could delete them as well. And we can also add in the sense of creating a gap.
Oh, okay.
Yeah.
So that, okay. That means, like, I guess the gaps will be at least the differences between the two.
Yeah, yes.
Okay.
All right, cool. So, how would you guys go about doing this? Would greedy work here? Can greedy work?
Yes.
Okay, that's one yes.
I mean, if you're looking to optimize.
Okay.
Yeah.
If we're looking to optimize it, we're going to use DP, but we could do it with greedy. Is that what you're saying?
I guess, as starting.
Okay. David is looking right into my soul.
It's a good thing to look at, huh?
Thank you. Yeah, Dembo, you were say something?
I don't know. I think I'd probably say no because like if you're at D and then the greedy choice at D can be something maybe like add a gap or something, but then doing that would probably cost you more in the coming sequences. I don't know.
Okay, so he said that if we were looking at A, adding a gap now might cost us in the future.
Yes.
Yes,
That
okay.
would probably be the best greedy choice at that point in time.
Yeah, okay. What do you say, Alejandro?
Yeah, same answer.
Okay, he agrees with Demba.
The goal is just to turn string A into string B into string A.
Yeah.
Well, the goal is to get the number of changes we would need to get.
Yeah, the changes to change B into A.
And you want the least amount?
Yes.
I feel like it could be done with greedy, but dynamic DP would be more efficient.
Okay, cool. David, do you want to say anything?
No.
No, David doesn't want to say anything. Okay, cool. So, you guys are making me think now, because I don't know. I actually don't know the answer to this question. I don't think it could be done with greedy. I think it is DP because your answer depends on the solutions to the previous subproblems, and when it's dependent on the previous subproblems, that's when you use DP, because greedy doesn't do that dependency. It just continues to peak. It picks the best one at the current point, so it does need some sort of I guess memory, you can call it, and that's where our DP table and dynamic programming comes into play. So yeah, then by what you said, it was right. That current action we take now might affect us in the future, so we don't really know. So it would have to be DP. I think David is searching it up. Am I right?
I know the answer.
What is the answer?
I don't want to say.
Am I right? I mean, if I'm wrong, correct me.
I mean, yeah, you exactly solved this with DP, and this could be done recursively, bottom up.
Yeah.
But it can also be done top down. Like from the
No,
recursive.
am I right in the sense that this is only strictly DP? It cannot be done with greedy.
DP problem.
Okay. All right. Cool. So yeah, it turns out that was right.
Actually, almost exactly like LCS.
Yeah. He said this is almost exactly like LCS. True. How you start your DP table is different. Your initial and row and column is not 0. It's the difference in that string. But everything else, pretty much the same, yeah. Because you're still looking in 3 areas. Minus I, minus j, and then minus j, and then minus I.
Or the way you initialize the top row is different.
Yeah, it's not 0, yeah. All right, cool. So now we all understand why it is greedy. Hello. Now we all understand why it is greedy. Oh, nice. I didn't see you. That was good. So now we all understand why it's not greedy, and we know what sort of algorithmic technique we need to use, which is DP. How would you guys design? What's the first thing you guys have to think about when designing your DP algorithm? Wait, Alejandro, don't say it. David, don't say it. Because I know he said it in your class. Oh, wait, Dembo's also in the class. Okay, now I'm figuring out Azar. I'm sorry. Okay, anyone say it. Anyone say it. Huh? That's actually correct? No, I'm kidding. All right, anyone say it. The question is, when you're first, so we already proved that we cannot use greedy, right? And we know that our algorithmic technique will be dynamic programming. What's the first thing we want to think about when designing our dynamic algorithm, dynamic programming algorithm? Not necessarily. Not necessarily. David is giving this hint, which means.
Yes. What does that mean?
No. Okay, but I'm looking for something else. The thing that he's. Okay, I know Alejandro and them say no.
I'm not sure if this is right, but I think it's probably like the subproblem.
Close?
Or the recursive calls to the problem.
Close?
The recurrence relation?
There we go, the recurrence relation. There we go. Yeah, so you want to figure out how each subproblem relates to a bigger subproblem. So that way you can structure it and you know what to call in your recursive function. Because that's how we'll start off. You might know your base case, which of course might be simple in this case when a or b is equal to 0. But what really matters is how they relate to each other. So you do need the recurrence relation. Huh?
No.
Okay. So what would the recurrence relation look like here? Damn, this is like more, okay. Yeah.
But don't you need to like first figure out what the subproblems are before you figure out how to relate them?
Yeah. So that's part of the recurrence relation. That's why you're using it. Yeah. So let me read. So A is equal to ace, B is equal to ape. Give me 1 second. Let me zoom on the camera a little bit more. Perfect. When the characters are equal to each other, what do we want to do? Do we want to make an edit in this scenario? No. Okay. Everyone in agreement?
What was the question?
When the characters are equal to each other, do we want to make an edit? No. That's 2 no's, 3 no's. No?
No,
4 no's.
no.
4 no's and I'm not gonna say. Okay. Yes. So
No comment.
no comment. Yeah, exactly. So yeah, that's exactly it. We don't want to make an edit because we already know they're equal to each other, and instead, what do we want to do?
Move on.
Move on. Okay. How? Do we want to move only one on and then not look at E and C, or do we want to move both of them? Both. All right. Why?
Because we already know that E and E are equal,
Mhm.
so we want to know the next two.
Yeah, exactly. We know E and E are equal to, so now what we want to fix or change is being the substring before those E's. That makes sense to everyone? Now we're looking at P and C. What do? We know they're obviously not equal to each other, right? So we want to make an edit. And here we have our possible edit choices. Do we know which one we want to pick?
Yeah.
We do? Do we know whether we want to replace it or create a gap there?
No.
For create a gap, isn't that to put in a new
Yeah.
relation, create a gap?
Replace.
Replace would be kind of like putting C instead of P.
Yeah. It would be putting C here, but I think you still, and then you only move one of them. I think you only move this top arrow.
Or you can move the bottom arrow too.
You should really look at this algorithm before doing this. I don't think so. I think it's when you replace it when you do I minus 1 and j minus 1. Then I think the other ones, when you do I minus 1 j and then j minus 1, that's when you're creating a gap.
This can't be recursively.
This could be, yeah, I did solve it recursively,
Okay.
and yeah, it could be.
I'm looking at mine, and I'm just looking at the table one.
All right.
What was the create gap for?
Create gap is basically, here, I'll give it, let me write the example I wrote for them. Okay. Let's say A was equal to ace, and then B was equal to AE. We could replace E and then turn this into AC and then create a gap. So this gap will be filled by whatever letter, which in this case will be E, and that's how we will get our answer. This has an edit of 2, because we replaced E with C and then created a gap which will be filled by the character E.
Is it possible to just create a gap in between, or no? We would have to replace it.
Exactly, that's the correct answer. Create a gap in between and then keep the E. This has an edit of 1. I think the camera can see that, can they? Yeah, they could, kinda. I already went over this, so it's fine. So that's how a gap will be like. Okay, so let's go back to this scenario when they're not equal to each other. Do we know what type of edit we want to make?
Can we like just like try all the different possible edits and take the minimum of them and add the cost as well?
Exactly. So one key thing here is that every single type of edit has a cost of 1. So if we replace it, that's going to cost us 1. And if we create a gap, that's going to cost us 1. So what Demba just said is that we don't know which type of edit we want to do. We don't know if we want to replace the character or create a gap. So why not just try both of them? Try both of them, and then take the minimum of each.
Right. Yeah. So when they're equal, just go.
Yes, diagonally. Yeah.
So you move both.
Yeah, -1, -1. Yes.
I have I guess a question. What if before we even like look at the strings and whatnot, what if we see if A and B have the same amount of strings, and we know for sure if any edits are supposed to be like done, it will be replaced.
Yes. So you're talking about the checking that the length are equal to each other. That's actually one of our base cases for this recursive call. And that's a pretty good catch. For now, I guess I don't have to continue going through this. Plus, this is recursive, so this could have taken a while. For now, are we all in agreement with the recurrence relation that if they're equal to each other, you just move on down? And when they're not equal to each other, try the different type of edits. We all agree with that? Okay, cool. So now let's talk about the first edit, which is replace. And let's see how that would look like algorithmically. Let's do it here. Replace. If they're not equal to each other, we want to replace them. How can we do that? Let's say we do replace them. What's the next thing we want to look at? Wait, I think you had your hand up first.
We would have to look at like what exactly are we changing for. Like if we're changing P to C, so we would have to look at that character.
Not necessarily. We don't really have to look at the characters. All that we really care about is that they don't match. Demba, you going to say something?
Yeah, I have a question. So like for the replace thing, which string are we trying to match to the other string? Does the replace depend on that, or are you just trying to get both strings to be equal, or are you trying to like convert one string to another?
Yeah, I think it matters in how you send the order into your recursive call, or how you create the DP table. Like which one's your row, then which one's your column.
No, like what I'm asking is like if we were to make a recursive call and we want to use the replace edit, are we going to like make two separate calls, one replacing the P with a C and
Oh,
another
no.
one replacing the C with a P?
No.
Oh, okay.
Yeah. So here, for example, in the replace, does anyone want to say anything before I give it away? Yeah, Azar.
Would the length of the two strings have anything to do with?
The length of the two strings is going to come into play for the base case. So yeah, that does have something to do. Yeah, you want to say something?
No, I was like, yeah, that was right.
Okay. So here, for example, what the replace is going to do, it's basically going to say that P is going to be set equal to C. And in that case, we can just move both of them on. We don't necessarily have to look out at the characters they are, but internally, we know that we're going to be using the replace edit, which is going to make them equal to each other, and now we can continue looking down. Did that make sense?
Just say it one more time.
Say it one more time. Okay, let me draw it out. Here, they're obviously not equal to each other, right? So we're going to be using the replace edit. Let's say we're going to be replacing the P, for example. This P is now going to turn into C. Now, C is equal to C. So we can move both arrows down. Did that make sense now? Yeah? Yeah? Okay, that's 2 nods. Demba, yeah? Did you see why I meant that you're not going to be placing this one to that one to this one?
Now I get it. You're not trying to make like both strings be equal, like you're trying
Yeah.
to get B to be A.
Yeah, because you're just trying to get how many edits, yeah.
So all the edits are going to be done on B.
Yeah.
You want C to pick like one string to be added?
Yeah, that's why I said I believe it depends on what you have, which string you have in your row and which string you have in your column. And then depending on that is how many edits you need to change from one to the other.
Makes sense.
We're only editing B.
Huh?
We could edit A too, no?
We could.
If A is shorter than B, we need to create gaps
Yeah.
in A.
If yeah, which goes back to Azar, what you said about the length.
So, for example, if A was ace and B was A C C E, you would create a gap in the first or the second C.
Wait, say that again, sorry.
If A was ace and then B was A C C and then an E, and you created a gap, it would just be it would be solved, right? Or like.
Yeah.
Is create a gap just like.
Just fill it in with whatever.
Oh, okay.
Yeah. Okay, cool. This is from Gary's lecture. In David, in the leak code problem, is it replace and delete?
Yeah, it's one so it's replace, it's delete, and it's insert.
Okay, replace, delete, and insert.
Yeah. In the
Geary had alpha and gamma, only two, because gamma represented the insert. Okay, let's add the third one. It's the same thing. But that is a better word. Instead of create gap, let's just do insert. Delete. Cool. All right. So going back to replace, do we all, yeah?
I know we're moving on to a different question, but like just out of curiosity, if you were to go with the create gap, how would you reduce the subproblem? Let's say you're C and E, and then you now want to create a gap, like you want to test the gap creation recursive call. How would you go about doing that?
So if we were to create a gap, you're talking about moving the arrows.
E wasn't there, so now we have to create a gap. How would we make the recursive call?
All right, let's see. Let's see which one moves. E. Okay, yeah, it's here. So you were to call create a gap on B, which basically is now going to internally change B to A gap E, and then what you move is the A arrow. So that kind of gives away the recurrence relation.
So you just move the A.
You only move one.
And then just move the
Yeah, so you only move one because you're checking creating a gap here. You can also check creating a gap up here, and then you leave this arrow where it is, and then you move this one. Right.
So why did you compare like A and C and not A and A?
Wait, what?
Like, why were you looking at A and C instead of A and A?
Yes. So we initially started at E and E, and we know they're equal to each other.
Oh, it moved from there. Oh.
Yeah. And then we move from A and C. Okay. So I'm pretty sure we just covered everything. Even though we were supposed to only do replace, I think we just talked about everything else. Mostly with Dembo's question about filling the gap.
What's the recurrence tree look like?
Huh?
Recursion tree, what is that?
Yeah, it'll be 3. It has a branching factor of 3. You in agreement with me?
I am agreeing with you.
Okay. I love it when we fight.
You always start strong, man. You.
Okay. All right, so let's try to figure this out. Let's try to figure out with replace. We know that they're different to each other, and we're basically going to set one equal to the other, and then move them both down, right? Yes?
But are you gonna change the question to A, B, E, or are you just gonna?
Oh shit, thanks. Thank you. All right. So here we said that if they do not equal to each other, That makes sense to you guys? Why we're doing this right here? Yeah?
And that there's a cost associated
Yeah.
when they're not equal.
Yeah. Yeah, this right here, they're all equal to 1. So here, this is basically just saying that if the current characters that we're looking at in A does not equal the current character we're looking at in B, we know we have to create some sort of what's the word? Edit.
Yeah, it costs.
Some sort of edit. That's it, right? Why was I trying to add something else?
You have to keep track of the cost, right? So that's.
Wait. Okay. Relax. Calm down.
Wouldn't it be N for both because we're looking at the same place?
What if they have different lengths?
Yeah, but it's replaced. Replaced will always have the same length.
That's
Mm.
the index between characters.
Yeah. Wouldn't it be same?
No.
Because they have different lengths.
Yeah, but we wouldn't be replacing it if it had a different length. That would be inserted.
No. That's just to index each. N indexes A. It's like I, and then N indexes B, so it's like J. And we might move those differently when we're doing recursion.
Okay.
So here, for here, even. Yeah. Okay. So they do have different lengths, but we still don't know what path we want to take or which edits we want to make. So we still want to perform replace, even if they're looking at different things. And then, of course, this is our finish first in the second one, right? Little hint, that's be part of the base case. Everything else that we never got to, you add. Because you have to delete those, right? And that's the cost of 1.
Inserting.
Yeah. Or not inserting, because you already replaced everything before it, so you just have to delete that. Like here, APES, you're going to change to ACE, right?
Yeah.
But then this, you use delete.
Okay, yeah.
But we don't know that if that's the most optimal edits we make. So we still have to try a couple other things in the different paths. All right, cool. All right, so if they're not equal to each other, we're going to replace it. And what are we going to look at next? What are we going to do next? Remember how we were talking about shifting the arrow? So what we want to do is n minus 1 and m minus 1, right? Yeah? Okay, 1, 2.
Do we want to explore recursively to see if we want to replace, insert, or delete it?
Yes. So right here, I'm not doing recursively. I'm just saying like what we want to do for replace. And then I'm going to use this information to do the recursive function later. But yes, it's exactly what you said.
But we're saying that they're not same, like they're not equal to each other.
Yeah.
So shouldn't we change that first before moving on?
No. Because we're just going to keep track of it by when we call the function again recursively, we're just going to add a 1. And we don't want to actually change the string. We just want to keep track of how many edits we made. So the number of edits. So we can leave it as if, but what we are keeping track of is how many edits. Yeah, the count of edits, yes.
And the minimum.
Yes, and then the minimum, of course. Well, of course, the minimum edits.
Do you explore it recursively for each chain?
Huh?
Do you explore it recursively down
Yes.
to the base case for each
Yes,
chain?
yes. And that's where it can get time complexity really high, but we use memorization, so yeah. All right, cool. I believe this is also going to be the same case for delete. I didn't do this thinking of delete, but if we were to delete it, we know that the other character will come back. Yeah, all right, let's try that. All right, so let's say we have A and E, and then APE, right? Obviously, E and E will match. So now what we're really looking at is P and A. If we were to delete it, oh, actually, no, it's going to be the gap one. If we were to delete it, we delete P. That means we move our arrow down to A, and we leave the top one as if. So notice here how only one arrow changed, right? It was the same thing for the gap, correct? When we inserted, we also just moved that one arrow. So what would that tell us for the insert and delete? Wait, I think she had an epiphany. Yeah.
Big brain moment.
No.
You know, let me break it
So
up.
would that mean for insert it would only be n minus one, and for delete it will only be n minus one, or the other way around? Okay.
That's actually why I broke it up. I think, yeah, if it's insert, you only move one. Let's say like the case is,
If it's insert, I think only above one moves. So n minus one.
yeah,
For insert we'll move
yeah. But I think the issue with that is that you don't know where you want to insert it. So I guess you are editing both to be equal to each other. You only, yeah. So, let me think about this. Hold on.
Can you write down the insert first and
Yeah, let's talk about insert. E and E match, so we're looking at P and then A. We don't know what edit we want to do next. We do know they're not equal to each other. If we were to do a insert or delete, would we know where we'll be doing that? We don't know if we want to insert something here or here. And we don't know if we want to delete something here or here.
no. But we're only changing D. We're never gonna change D. It's always gonna be insert, delete, and D. Never D. Because there should be one string we're comparing everything to.
Is there one string? Was I right when I said that? That we're comparing everything to? Ah, crap. Give me a sec. In my algorithm, I'm doing it.
It wouldn't make sense to be changing two different strings
Yeah.
and not having one fixed one.
Yeah, that makes sense.
I think so too, because it makes sense to edit both strings if you have the gap thing, but without the gap thing, I don't think it makes sense to edit both of them.
The thing is, if we were to change both strings, then it doesn't make sense what we're looking for. Then we would have so many like edits.
Yeah, but would we have knowledge of which string to change specifically? Because if we're doing it recursively, we're just trying each and every single edit for both, no?
Wouldn't it help, I guess, if we know which one's shorter? I guess?
Yeah, that comes.
Also big gap.
That comes into the base case, like the everything else. Crap, I don't know if I'm right when I say this. Yo, this almost looks like a U, huh? if you know what it spells.
Oh my god.
Shall not be named.
Damn it, man.
You could just review the the definition of the algorithm real quick to see if we're turning
Yeah,
A
let's do
into
that.
B or D into A. Like, just
Let me
real
just look at the problem description.
Just look at the question.
Yeah. Yeah, okay. Minimum number of operations to convert word 1 to word 2. So yes.
Yeah.
Wait, word 1 to word 2.
That's A into B.
Okay, so A into B.
Or, well, no.
Yeah. Wait, convert 1 to 2. No, yeah, this one to this one.
Arbitrary.
Yes, so that's what I think.
Yeah, you're totally right. That's why it doesn't. Oh, that's why. Okay. Yeah, it doesn't matter which one you choose. It's exactly that. You're totally right. Whether you choose A to B or B to A, it doesn't matter. But yes, you were right. One of them does stay constant, and then the other one we change to that one. So, going back to what you said, if we're inserting, no, here we will be deleting. Yeah. Okay, yeah, here we'll be deleting P, and then P will be going away. We just do an X over top of it. And then it comes down to A, and then we know that match. And then that will give us a cost of 1, which is the right answer here. If we were doing it the other way around, that's why it doesn't matter where we do insert or delete, whether we move this one down or this one down.
It matters. 'Cause
But
it-
we can do either A to B or B to A. And then A to B here will be delete, but B to A will be insert, or the delete of 1 to 1 will be the insert of the other to the other.
So you pick one of them to be the standard one or the one.
Yeah. So either way, it doesn't really matter, because you're either going to be doing delete or insert, and since they both have the same cost, it will give us the same thing.
Don't you have to be consistent with the one you're editing? Like once you start editing one, don't you have to be
Yes,
edit that one?
but if you continue that way, and then you do it the inverse way, right? Let's say we're trying to do A to B. We'll be inserting here, but let's say we're trying to do B to A, we'll be deleting. That's what I was trying to say.
Yeah, so the entire time you will be editing the same.
Yeah, it's the same thing. But the insert from A to B will be the delete of B to A.
That's a slash. That's why you
Oh
wrote
yeah, it
insert
would be,
slash.
yes.
Huh?
That's why you wrote insert slash.
Yeah, because it's the same thing, but it just depends.
Yeah, it's for the reference point.
Okay, cool. That makes a lot of sense. All right, so now let's talk about that. Let's say we're trying to do A to B, right? This doesn't match, so we'll be inserting. We'll be moving this one down, and this will now become A underscore E, and then they match, so we're done. And then this underscore represents the gap, the character that we inserted. But now let's say we're trying to do B to A. P does not match A, so we delete P, and then move this arrow down, and now they match. Do you see how it's insert for one way, but delete for the other way? All right, cool, nice. That was good. That was fun. Yeah, that makes a lot of sense. Because initially in the algorithm, I did it with the length of this one in the rows, but then when I tried to do it recursively, I used the length of this one for the rows. But it gave me the same answer, and that's why, because they all have the same cost. So that's cool. Hey, Hermes. Okay, cool, nice. So for insert, Ricky is ready here, I guess. Let's say we're trying to do A to B, or no, B to A. It's n minus 1, and m stays the same. Right? Was this with what you said, Kunza?
Yeah.
All right, cool. And then delete is with the exact same thing. All right, cool. And then delete is with the same thing, but the other way. Delete. It's just going to be n minus 1. So now I guess, that really helped. That little exercise that I definitely planned really helped to understand all this, huh? So do we get why we want to do these operations for these types of edits? So how many operations here do we have? How many recurrence relations, I guess?
Three.
3?
One for each.
Yeah. So we would have 3, because none of these really match with each other. So unique, we have 3, which is the same count of edits. So we can add that to our algorithm. We know that if they do not match, we can kind of generalize this. If A of n does not equal B of m, we want to try all of those. Let's try n minus 1, n minus 1. Let's try n minus 1. And let's try n minus 1, m. Let's try all these. And of course, that cost, like David said, we need to add all of them a cost of 1. And then choose the best one. Do you guys see how this is tying in to recursion? Because if they're not equal to each other, then recursively, we want to call these and then choose the minimum. If they are equal to each other, then we just return n minus 1. Well, not return. Try to solve the smaller section.
Well, aren't you doing that anyway in the
Yeah.
second line?
Yeah.
Oh, okay.
I tried to, I was looking at it too, and I was trying to figure out a way of, so I don't have to write them both. But eventually you will have to, because you need to add that plus 1.
Oh, true.
Yeah.
So we're replacing anyways?
So this if they match. And remember replacing, yeah.
We'll move on anyways.
Yeah. Replacing is the exact same thing as matching, but you just need to add 1.
So we're not adding.
Yeah. Okay, David is looking concerned. I may have said something wrong. Let's see. Replacing is the same thing as they match. Adding cost of 1 to replacing.
You're doing recursively both facts that's plus 1 to see it in that
Yes.
direction.
Yes, because you're replacing the letters that didn't match, and then you want to figure out everything else. Yes, you do. Yeah.
I've never tried it.
Yeah, you need that in the algorithm. Like that's how I wrote it, and then I look at the discussions too, and they also had it. So there's no way around it.
Oh, okay. So, and you get the minimum of all.
You get the minimum of all of these.
Okay.
Okay. Oh, David, you don't have to call me a genius and the smartest person you know, please. Yeah, Demba.
Out of those 3, which one is the delete and which one is the insert?
Yeah. So the delete and the insert, in this case, we don't really know. We don't know which ones we're converting from one to the other. We don't know. Well, I guess here we do know, because we're doing these. But since if we do know, then we know that the insert is going to be this one, and then the delete is going to be this one. But let's say these were variables that you pass to your recursive function. What you can pass it whatever order, it will still give you the same edit distance. Because remember, the delete of one way is the insert of the other way. Cool. Woo, gotta step it up. Okay, so now we know we need to take the minimum of this. This is really ugly. I'll rewrite it later.
Return min or return bottom.
Yeah, I'll write the base case up here. Oh, damn, the mic is close to me, so I think they heard that.
Yeah.
You want me to make a big deal out of it?
Yeah, no worry.
It's fine.
I was just trying to. No, I'm gonna make a big deal. I'm gonna go. Language.
Are you gonna get dropped by Google?
Yes, we're gonna get dropped. Our sponsors are gonna leave.
It's gonna be the Yahoo.
Sponsor, we're powered.
Our power is going to
Our power bill
Oh, in the video. Oh, thank you.
No, I mean like, can you move?
Oh,
it?
this.
Yeah.
Oh, that's what you meant. Sorry.
Right. Oh, yeah. Wait, it will be the min plus 1.
Yeah, you're right. I forgot the +1. Thank you. I'm easy to zoom out, bro. Thank you, Kunza. Okay, cool. Else, if they do match, return n minus 1, n minus 1. We're building out our recursive function right here. What will our base case be?
Okay, an idea.
He has an idea.
If, well, actually, if n, oh wait, so we're actually indexing n. So that means that 0, and that means the length of that so far is 1. So if n is less than 0, return m.
Exactly.
Well, actually, if they're both less than 0, return 0.
That's a lot of ifs and else ifs. So
I
we can
know.
simplify it just a little bit, but it's exactly what you're saying. If, for example, n is equal to 0 and m still has some characters, let's return m. Because those remaining characters in B, let's say m was here, so those 2 characters, we want to delete. And by returning m, that's how many deletes we're going to make. The remaining characters. So if n is equal to 0 or m is equal to 0, return max of n or m.
Are we doing 0 indexing of the string?
Yes. No, we're calling this recursive function with n and m equal to the length minus 1.
I have a question. Can our base case be like, for example, b is equal to a, and then you return max?
If b is equal to a,
Yeah. Because like we're
So this
still
else?
making them.
because if they're equal to each other,
Yeah.
we might still have some strings, right? There's still some things to solve before it.
But we're not taking a length. We're like exactly the same.
Oh yeah. Oh, okay. Yeah. In the beginning, if we want to prune this recursive call, then yeah, we can just check if b is equal to a in the beginning. If it is, just return that, and we don't have to do any real DP work.
So can't that be also the base case?
Here, this is our recursive function, so we don't want to add it to our base case, because this function is going to call itself multiple times, and we only have to do that check once. So we might as well do it all the way in the beginning.
I think it's gonna grow exponentially.
Yeah, you're totally right. This is going exponentially. So what can we do to solve this?
It rhymes with Nemo.
Okay, David says it rhymes with Nemo.
N and M.
Yeah.
What? How does it rhyme with Nemo?
Okay. Replace the n with see what it is.
Yo, he's saying it rhymes with Nemo, but replace these letters.
Or replace, see, like the problem.
Okay, like the
What's
problem?
difference between Nemo and B?
Okay. Someone please just say the answer.
Brain is too big, we can't comprehend.
Yeah, he's on another level. Kunza, you said it during his lecture. To make this algorithm efficient, what do we need to add?
I said to check the length of the strings.
During his lecture, you said something that starts with the letter M. Memoization. Exactly. There's going to be...
It rhymes with Nemo.
It rhymes with Nemo, yeah, memoization.
It's spelled like Nemo. It's spelled like Nemo.
Yeah, if you flip letters in this word.
And I can't.
Nemoization.
I put it in the like that. Nemo. You got it, right? He gets me. He gets me.
I get you.
You get me too?
Now that I know what you meant.
The press, they get me.
No, I also understood them, but why would he? No, I understood you, but why would you say that it rhymes with? Why not you say like
Okay.
it doesn't rhyme with? It rhymes with something else.
You know what? It should be emo, because there's a vowel over there.
Dude, I
E
don't
should be accented.
I don't know what you're saying.
You know what I'm saying?
No. You're saying it rhymes with its word if you change the word.
This is too technical.
Okay, whatever. It's fine. So yes, we want to add memoization. Why? How does memoization help our this recursive function?
Something in check.
To keep something in check. Then, but you gotta raise your hand, or okay, yes, yeah.
No, I wasn't, but I think because like at every N and M, if we have already calculated what the minimum edit distance is, it's not gonna change, so we don't need to calculate for all the recursive calls.
Exactly. Because is that what you were saying? Yeah. Okay. Yeah, we might have already solved. We might be on a subproblem that we've previously solved. So by keeping track of the subproblems we've solved, we can avoid redoing the work. If we're on a problem that we've done before, just return what that previous work returned. I see something's going on in chat.
Replace base, keep A.
Who's Aliso?
Monkey business.
Are you Aliso?
I like
Okay. All right, so yes, we want to add that exact work right there. Let me move this up. Or m is less than or equal to 0. Return max of n or m. And then if in our DP table or our memoization table, if we already solved subproblem n, m, so let's say we initially filled that table with -1s. If it's not equal to -1, we know we've done it before and that we've solved it. So let's not redo the work. Let's just return what it initially solved or came out with. So now we added our DP table to the base case to not redo work. How can we fill up this DP table? Hold up, I think Alejandro wants to tell me. It's similar to the LCS problem. Doing it recursively, like it's all pretty similar, filling up the DP table.
You would check if you get to the end of the string that you don't want to change, right?
Wait, what?
No, you're. No, seriously.
No, it's fine.
Yeah.
Okay, so you're good? I asked something else?
I'm
Okay.
just kinda like out of it for this time.
No, it's okay, don't worry. Dembo, did you want to say it?
No, but
Okay.
but I think like since we're like just moving up and left all the time, like the -1 and -1, if we like fill it in a row major other, it would
Yeah.
affect the solution.
Yes. For doing it iteratively with for loops, row major does matter because those are the things we're looking at. To the top left, so let's say we have a table. We're currently right here. We're going to be looking at this, and then this. So for doing that table, row major is the proper way of doing it. But for recursively, what I was trying to get to is that we're using our DB table in the beginning as a base case. But to actually fill that DP table, we need to put it.
I wanted to say that M in the DP looks like an N.
That's what you want to tell me?
Yeah,
I thought you were saying the answer. That's why I pointed at you.
Well, I'm helping you.
Okay.
And the other one as well. All right. The one with. Yeah, no.
Okay. And we're gonna put it.
Okay, just fill up DP and M each in the if statements.
Each return, yeah,
Yeah.
pretty much, yeah.
And then return outside of yourself.
The what? No, can you repeat that?
Okay. Basically, we're going to fill it up there, right and below as well.
Yeah, yeah.
In yellow.
I turn around for something else, but yeah.
Straight up return.
Yeah, we're gonna do it after we get done with it, and then we'll return whatever after we get it.
So we want to save whatever this gives us, whatever work this gives us in our DP table, so we can call it back later on. Once we save it, then we can do it outside. Yeah, let's just do it outside. Once we save it, the solution for that sub-problem, we use return it. We're doing the exact same thing. Previously, we had return this, which did not change at all, or this, which also did not change. Only difference, that we're first storing it, and then we're returning whatever we stored. So in a sense, we're returning either this or this. Is the confusing part the fact that we moved the return out from both of them?
My question is this gonna be one math variable?
Yeah.
Yeah.
Yeah. This is all one function.
You don't have a name for it.
Yeah, I didn't write a name for it because I was doing it like this.
That's the call.
So.
The calls are right there.
Even in Java, it would be one function?
Yeah.
Okay.
Oh, this is one function.
I think I was confused. So this never changes any of the strings. This just counts how many changes it makes. Okay,
Yeah.
sorry. That's why I was confused.
Yeah, yeah.
Let's say N and M are negative 1. Right? So then,
I did less than or equal to, so you can,
it will return max between negative 1
yes,
and negative 1.
which is the remaining characters.
Okay. So we don't
This
need
works. That's how I did it. It works.
exactly like this?
Yes.
Okay.
And
That's
it
what
has
I
that
was
in,
saying,
yeah.
because
So,
I was like, there's not one function, there'll be two functions.
What's the
one that's
condition?
called, yeah, one particularly, yeah, the recursion is only happening in one.
That's what I wanted to ask.
What was the part?
Because I thought this was like a whole one function, not two different functions.
No. This is all this work right here is one function.
But the creating the DP table would probably be creating a function.
Okay.
that has
Oh,
to-
yeah.
that's what you-
Yeah. Like getting the strings, created the DP table, and then calling this function. That one's in another.
Yeah, yeah.
This is just your recursive function.
Okay, that was one.
Okay. Yeah.
Because I was like, I don't know where the DP comes from.
Yeah. That comes from outside, where we instantiated. Yes.
What's the condition that makes it so that you reduce the work? Because I remember also being confused right there.
Yes. So we're saving the work we've done for this sub-problem. If we see that sub-problem again in the future, it's going to be here. Because initially, our DP table is just filled with negative ones, which that can never be an answer. The minimum is 0. So we know negative 1, it means that we have never touched that state before.
Yeah.
But if we updated that state and we see it again, we know it's not going to be equal to negative 1. It's going to be equal to something else. And that's when we just return it. So we return that previous work, and we never do this.
So if it's all filled up, it's
Yeah. It doesn't necessarily be all filled up. It's just that that specific state is filled up.
yeah.
Yeah, we've done it before. So that's it. This is our recursive function. Do you guys, I'm going to challenge you guys this Saturday, and it's definitely not because I'm running out of time. This Saturday, with this problem is going to be part of the competition. Try to do it using the DP table.
So try to solve it without using recursion.
Without using recursion, do it iteratively. Little hint, it's the exact same recurrence relation. Unlike the other problem, but whatever. You guys think you can do it?
Yeah.
This question is actually edit distance. This is a really popular question for DP. It's on LeetCode, so you know companies are using it. So if you know how to solve it both ways, which I think you guys can do it recursively. It was very interactive, so I know you guys can do it recursively. If you could do it using a DP table as well, that'd be amazing.
You mentioned that unlike the other problems, like is there like a problem like the recurrence relation that solves the recurrence relation you can use to solve it recursively is different from the recurrence relation you use to solve
Yes.
it iteratively?
So that other problem that I said the recurrence relation is not equal to the recursive recurrence relation, that was the problem that the second problem Gary gave. Ricky did it recursively,
But the recurrence relation
but the recurrence relation when we implemented pretty much the same thing, it wasn't working. I don't know if we did it wrong or something, but it was coming out different. So maybe there's something else to take into account. But that's because that's a 3D dynamic programming question, a 3D array. It could be solved with a 2D, but I think it takes into account something else. I think the majority of it is going to be the same, but the calculation is going to be a bit different. Like the main idea of it. Yeah.
What's the difference between using a 3D array and doing something similar to what Giri did when he fully fleshed out the LCS problem, using like kind of overlays, like multiple arrays to pretty much analyze the DP table that he made, if that makes sense.
Oh, okay, I see what you mean.
Yeah.
That one's still 2D. It's just that the value in that table is now a tuple. That second value will tell you where you need to go to find that greatest common subsequence. So that's still 2D. It's just the value changes. For 3Ds, the value is an array. For that one, the value was a tuple. You can also think of it as an array with 0 and 1, but that array doesn't really change. Like that's a constant value, and it's not equal to n. If it's equal to n, then it would be n by n by n.
I don't know if this is cheating because you said you're going to give the question out on Saturday, but like what would be the base case if we were to use a DP table?
Yeah, that's a good question. I do want to tell you guys that. For the DP table, your 0th row and 0th column, the top coordinates will be equal to 0. But then this is saying that, let's say here we have A, right? And then here we have B. So here A will be length of 3. Like that. In the 0th row, let's say we're saying that A has a size of 0. So everything else is going to be like that. We're going to initialize it like this instead of just zeros.
The top will be one insert, right? And then
Yes.
two inserts, and then three.
Exactly. Exactly. And then everything else you still want to look up here, and then up here. But that's the only thing you need to initialize in your DP table that you need to keep in mind for iteratively. Okay, cool. So that's it. 4:44. We're a minute short, couple seconds. Yeah.
What about the binary search?
That's true. If you're on campus today, go to the intern panel that DSC FIU will be live streaming and holding in person. GDSC FIU, sorry. It will be happening in room PG 6 116 at 5. It will last around an hour, or maybe an hour and 30 because we hang out around after. And then the binary search night, we're just going to go together, random room, do some binary search, and then some programming questions from 8 to 10, yeah, in PG6. A random room in PG6.
When is the binary search night?
It is tonight. The binary search night is tonight from 8 to 10. It's very informal. It's just a little tradition we're trying to make. It will be happening bi-weekly. Is there an issue?
Yeah,
No?
so
Okay. 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 Cool.
it's just he didn't announce it.
Huh?
Like you didn't say it was tonight, so I didn't
Oh, okay. Yeah, it's tonight. Thank you guys for watching. Hopefully this helped. Also, this helped you guys too. Thank you.